The development of modern supersonic aircraft requires identifying safety-critical hazards during the earliest stages of design, particularly for fuel systems exposed to extreme thermal and structural loads. Conventional document-based zonal safety analysis methods are limited in their capacity to identify hazards at the conceptual design phase, leading to increased redesign costs and heightened safety risk. To address these limitations, this study proposes an integrated framework combining computer-aided design and model-based systems engineering. The methodology utilizes CAD for geometric modeling and thermal analysis within the 3D Experience platform. These spatial models are linked to functional architectures developed in Cameo Systems Modeler using SysML. Interoperability between the CAD geometry and the MBSE architecture is maintained through the step data exchange format. This closed-loop process allows spatial design information to inform the functional safety analysis, which in turn guides iterative design refinements. The framework was applied to the SA-24 Phoenix conceptual supersonic aircraft. The system architecture incorporates 8 integral tanks distributed across the wings and fuselage to optimize weight distribution and center of gravity management. The primary subsystems include a redundant dual pump transfer configuration, multiple venting pathways for pressure regulation, and a digital fuel quantity indication system. Zonal analysis within the CAD environment identified critical spatial interactions, such as the proximity of fuel transfer pipelines to high-temperature environmental control system bleed air ducts. These interactions were then mapped into the MBSE environment to evaluate potential failure propagation paths. Safety performance was evaluated using functional hazard analysis, failure modes and effects analysis, and fault tree analysis. The integrated framework identified key risks, including fuel vaporization due to aerodynamic heating, overpressurization from venting failures, and structural fatigue leading to leakage. To mitigate these risks, the study evaluated advanced composite insulation, redundant venting pathways, and reinforced sealing techniques. For example, FTA was used to analyze the no fuel-to-wall engine scenario, identifying root causes ranging from ice formation at high altitudes to electrical failures in the pump system. These safety requirements were benchmarked against EASA CS25 airworthiness standards. Quantitative results demonstrate that the CAD MBSE framework significantly enhances early-stage hazard identification. Implementation of the proposed mitigation strategies resulted in a 40% reduction in the risk priority number for thermal hazard pathways, a 35% reduction in overpressurization risks, and a 50% reduction in the probability of fuel leakage. Furthermore, the integrated workflow reduced the conceptual design iteration cycle from 12 weeks to 9 weeks, representing a 25% improvement in development efficiency. This research establishes a scalable methodology for the digital engineering of safety-critical aerospace systems. Future work will focus on extending this framework into a digital thread architecture, incorporating real-time operational data and high-fidelity simulations to support full aircraft certification.